All right, so here we're going to be using integrated rate law. So we're talking about a first order reaction. Now here's the reaction, the decomposition of ammonia to nitrogen and hydrogen gas. And it says at a certain temperature, the rate for this reaction, the rate of this reaction is first order in NH3, which is our only reactant, with a rate constant of this. So here's K. And of course they specified that at a certain temperature because K changes at varying temperatures, but will always be the same as long as the temperature doesn't change for this reaction. They say suppose a vessel contains ammonia at a concentration of this, so it's initial concentration. Calculate the concentration of NH3 in the vessel 73 seconds later. So we may assume no other reaction is important. So this is different than the previous half-life examples because we're not given a half-life. We have a time, 73 seconds. We have an initial concentration, and we have K. And they say, okay, given this information about this reaction, K, the time that we allowed to go, and initial concentration of this, what is the concentration at the end of this 73 seconds? So, of course, we can't use half-life for this, but we're going to have to use what we call integrated rate laws. So we know that this is a first-order reaction. And we could simplify the rate law for a first-order reaction that only has one reactant as the rate is equal to K times A to the first power. Now, we're not going to get into how this is derived, but using calculus, and I believe it's talked about in the textbook, they show the steps. Using calculus, you can integrate these integrated rate laws. So these are derived using calculus from the rate law for whatever order the reaction is. So there's a different integrated rate law for different order reactions. Matter of fact, in your notes, you have a first order integrated rate law, a second order integrated rate law, and a 0th order integrated rate law. We're only going to be using the first and second, the two most common types of reactions in these problems here. Okay, so in order to solve this problem, of course, we're going to use the integrated rate law that I've placed here for you, and you have it in your notes as well. These rate laws may take up various forms. You may see in your notes that it has the one form of the integrated rate law. Looks like the formula for a line. It's a linear function, but this one has just been rearranged here, rearranged to this format, which is going to be useful for you for these problems. So how do we approach it? Well, let's write out what we have. We're given a concentration of A, and this is the initial concentration. So that little not sign, that little circle, indicates initial when it's a subscript. So the initial concentration of A, and in this case, A is ammonia, but we'll just leave it A. We only have one reactant, and there it is. The initial concentration is equal to 0.280 molar. We're also given a time. So at a certain time, if I stop, what would be the new concentration? Now, of course, it's going to be less than the initial because ammonia is being consumed in this reaction. So the time is 73 seconds. And also we are given K. 0.0178 seconds to the minus 1. Notice the units for K. This is a first order reaction. The units for K is seconds to the minus 1. Different than what we've seen for third and second order reactions. Okay. All right, so these are our givens. We can see that we can plug this straight into this formula. What are we solving for? Well, we have K. Here's K. We have T, here's T, we have initial concentration. We are solving for final concentration. There's no F there, but if you like, you can put that there. We are solving for the final concentration of ammonia, okay? Normally, there is no F there. Just read that as final concentration. So we're going to plug this into the integrated rate law to solve for the concentration of A, or ammonia. So let's begin. We'll take the natural log of ammonia, and I'm not going to placed the initial concentration yet. I'll do it one step at a time, but we know that's initial, is equal to negative, don't forget the negative sign there, negative K, which is 0.0178 seconds to the minus 1, times the time, 73 seconds. Notice that the units of time cancel. Perfect. Okay? Put that into the calculator, I get negative 1.2994. And the units again have canceled out. So natural log of concentration of ammonia over the initial concentration is equal to that. So now let's continue. What do we have now? We have the natural log of this is equal to this. The question is, how can I get rid of this natural log there? On your calculators, you will see the ln button. On mine, it's under the log button. So what we have to do now, to get rid of this natural log here function, we have to take the inverse natural logarithm of both sides. So how do we do that? Well, on your calculator, you'll see second button. If you hit second, and if you hit the ln button, the natural log, you'll activate the inverse natural logarithm function. And it should be this right there, that function. Okay? So that's what we're going to do. So what it'll look like is, if I do that to this side, natural log goes away, and I just end up with NH3 over NH3 initial. And it's going to be equal to, look, if I take the inverse natural log, what it does is change this to this, e to the negative 1.2994. Okay? So I put that into my calculator. I hit second ln, and it goes into my calculator. An e pops up, and I put the power as negative 1.2994. What I get is 0.2727, and I'm going to leave it there. So I have the concentration of ammonia at this specific time over the initial concentration of ammonia is equal to 0.2727. Now let's substitute the initial concentration. The initial concentration, as we have here in our givens, was 0.280. 0.280. So let's go back. Let's place it here. Concentration of ammonia at 73 seconds over 0.280 is equal to 0.2727. Now, how do I solve for this? Easy. I multiply both sides by 0.280. That goes away. And I get the concentration of ammonia is equal to times 0.280, 0. to two significant digits, it would be 0.076. Now, the units here, I did not write molar there. I should have. So when I bring the unit up like I'm supposed to, I have the unit of molar left. I'm going to multiply this times this. And that is my answer. Okay, now let's check. Is this concentration less than our initial? Initial was 0.280. This is 0.076. Yes, it is. So that's perfect. It should be. Okay, so we use the integrated rate law, but we have to make sure we use the correct integrated rate law. We need the integrated rate law for a first order reaction. We also need to always ensure that our unit of time is going to be in seconds. Why? Because we need it to cancel with the seconds in the units for K. Now, if K is given with other units, for example, hours to the -1 or minutes to the -1, then we need to make sure that time is also in hours or minutes. So the units for the time and the K always need to match up so that they cancel out like they did here. And I'll also, just for you all, I did mention the equation for first order reactions can be presented following the equation of a line, y equals mx plus b. So you could also see this integrated rate law written in this form. The natural log of the concentration of A at any time, you can put that t there or not, is equal to negative kt plus the natural log of the initial concentration of A. So this integrated rate law is just a rearranged version of this. And this one is the y equals mx plus b format here.